Good afternoon. Good afternoon. I am Pierfrancesco Novielli, and I am truly grateful and excited to speak in front of this audience. I apologize now if my English will not be perfect. It's my first conference in the US. Today I will present the work done by the team in the development of the algorithm that we submitted in the preterm DREAM challenge. The talk is entitled Ensemble Machine Learning to Predict Preterm Birth from Vaginal Microbiome. I will start from the outline of the talk. After an introduction to the problem of preterm birth, I will show you the preparation of, and the preliminary steps of preparing the data for training the model. Then I will describe the workflow of the analysis by showing you the flowchart, and I will focus on the machine learning model and on the ensemble strategy. Finally, I will describe the evaluation of the models on our test set. So, globally, about 11% of infants every year are born preterm, more or less 15 million births. Preterm birth is defined as a birth prior to 37 weeks of gestation, instead early preterm as a birth prior to 32 weeks of gestation. Preterm birth is a major cause of neonatal mortality worldwide. In fact, preterm birth have higher rates of neonatal deaths and have long-term health consequences for some children. Increasing studies show that the vaginal microbiome plays a significant role in adverse pregnancy outcomes, such as preterm birth, and there are significant differences between the vaginal microbiome of patients who deliver at term and those who deliver prematurely. The objective of the challenge was we had the task 1 and task 2. The task 1 has the objective to predict the risk of preterm birth, task 2 to predict the risk of early preterm birth. Our model worked better on task 1. We ranked in the second place in the task 1 and on the third place in task 2. The data that we have that we considered were longitudinal data, and that is in the sense that there were multiple samples collected from the same individual at several gestational weeks. So first we filtered all the dataset, the dataset in order to exclude all those samples that were collected after the 32 weeks for task 1 and after the 28 weeks for task 2. Because we knew that for the independent test, there weren't these samples. So we have reduced the number of participants for task 1 and task 2. And because of the complexity of the problem, we used a machine learning approach based to both the meta information such as ethnicity, race, and gestational week, and also we used data on microbiome. For what concerns this type of data, we used community state types that groups the specimen according to the composition of vaginal microbiome. We use also the alpha diversity matrix that describes the enrichedness and the variety of the organism in each specimen. And the most consistent part was the relative abundance of phenotypes. We had 3 matrices for each for the different phylogenetic distance. So we built a model that take in input 3 different matrices, data 1, 2, and 3, 1 for each phylogenetic distance. Then we had concatenated to these 3 data also the information about the community state types, the alpha diversity, and also the demographic information. The main problems that we identified and that needed to be addressed in the implementation of the various models were the imbalanced classification. That is, the imbalanced classification is a problem of classification when there is an unequal distribution of classes among the training dataset, and we handled to this problem with the use of an algorithm of data augmentation, such as SMOTE, that I will explain later. And another problem that we identified is the so-called curse of dimensionality, because there were a lot of predictor variables respect of the number of the samples. To handle with this problem, we chose an appropriate machine learning model, random forest, and also we used also a feature selection algorithm, Boruta. This is the workflow of our model. We built 3 independent models, one for each data 1, 2, and 3, so one for each phenotypes matrices. After the filtering module, we did the feature selection with Boruta. Then there is the module of SMOTE, that is the module who performed data augmentation. Then there is the random forest classification, so the random forest classifier. Then we had different prediction for each samples that we have grouped together to obtain one prediction for each participant. Finally, the 3 output for one of the each data are put together with an appropriate ensemble strategy to have the final prediction. So for each participant at the final of the model had the 3 final output that we have put together. SMOTE is the algorithm that performs the data augmentation and stands for synthetic minority oversampling technique. That is an oversampling of the minority class to account for a class imbalance. But how a sample is generated? A sample is generated by, we have to fix a sample of the minority class. We have to look at its k nearest neighbor, and the new sample will be generated by this equation, so by an interpolation between the sample, the original sample, and the new its k nearest neighbor. The model we have chosen is the random forest, because when the random forest build its decision tree model is decision trees. These decision trees are built by a random subset of the original features. So the number of features are reduced. Moreover, we tried also to use a feature selection algorithm that is Boruta. Boruta belongs to the wrapper method and of feature selection, and this method is built around the random forest. First, Boruta duplicates the original dataset to create the shadow features. Then random forest is trained over all the dataset and assigned a value, a z-score, for each feature, depending on the importance of each feature. So the algorithm uses the shadow feature maximum z-score as the threshold value, and the original features with the z-score higher than the maximum shadow feature are deemed as important, while those with the z-score lower are deemed as unimportant. For what concerns the ensemble strategy, how we have grouped the prediction from by sample to by participant, we took the average of the probability score of all the sample related to the same participant. We tried also other strategies, such as to take, instead of the mean, we took the maximum probability, but this is the model we performed better. For what concerns the final prediction, we took the three output of the three independent models, and the probability score of the subject was taken by taking the average of the three probability scores, and the classes associated is taken by depends on the on this probability that is calculated, and we chose the threshold of 0.5 to take it. There will be. We also tried other methods to put together these results, this output. For example, we tried to classify a participant as preterm if at least one model over three classify it as preterm, or to classify it as preterm if at least two models over three classify it as preterm. But this is the best model. So in this slide, I reported the best model results obtained with a 0.9, 0.1 Trent split repeated 20 times. In the figure on the left, there is the mean of the ROC curve together with its standard deviation. Instead, on the right are shown the box plot of the distribution of the other metrics, such as accuracy, sensitivity, and specificity. As you can see, the sensitivity remains lower than the other metrics. This means that our model is able to better classify the women who give birth in term. In this work, so we explore the predictive models of random forest-based ensemble methods. And we thought that the definition of a threshold and the probability value assigned to each subject is a crucial aspect in evaluating the performance of the testing pipeline, and it's a point that needs to be investigated. For example, we use the default threshold for classification 0.5, but other methods could be used for finding the optimal thresholds. For example, the maximization of Newton's J statistics, that is the difference between true positive rate and false positive rate. But applying these methods, the sensitivity became lower and the specificity became higher. So we thought that the sensitivity is a very important parameter to evaluate a model, so we have to investigate other threshold optimization. Finally, in this slide, I introduced the team that conducted this work. It's a multidisciplinary team from University of Bari, Italy, and it is made up of microbiologists and from physicists such as me. Our research is focused on the development of artificial intelligence models. That's all. Thank you for your attention.
So I'm curious so the timing and sampling of the samples was an important factor that the previous team had used for prediction. Did you include time of the samples?
We included. The question is we include in the information about the time of the sample. Yes, because in the random forest classifier we use the gestational weeks as a feature, as a variable, so we considered it.
Thank you again so much for your work. I was curious, we saw a lot of teams doing some data filtering, feature pruning, things like that. And from what I understand, your team had filtered the data so that for the task one, we're only using samples that were collected up to
32 weeks.
Right.
Yes.
And for the task two, which was very clever. I think we did the same thing with validation data, but for different reasons. I was wondering if you could go a little bit more in depth into how your team chose those as your thresholds for sort of like the collection cutoff for your treating data.
We made that filtering because we knew that in the validation independent test wouldn't be those data. So we thought that was the best choice to do.